So, Malte Renken.
Hello, can you hear me?
Yes, we can hear you. Can you share your slide?
Can you see them now?
Yes.
Okay.
Let me. Yeah. Okay. So our second speaker is Malte Renken, and he will talk about temporal pathfinding in the presence of delay. So again, we have a talk which talk about delaying some temporal graph. We are a bit late, so I will shorten the introduction to this. Please, the floor is yours.
Thank you very much. This work I'm presenting is based on two papers which are jointly authored with Eugen Füchsle, Henrik Malte, who is also here today, and Rolf Wiedermeier, who sadly can no longer be here today. And I want to start with a little bit of motivation. I guess many of you are aware that prime examples of temporal networks in the real world are kind of transportation networks, be they like public transport networks for passengers or for freight, because these networks, of course, have a temporal nature, and they are also scheduled in advance, typically. So you have some schedule you're following, and you know when these connections will be going in advance. But unfortunately, these schedules often don't survive contact with reality. So I guess we all know that trains are delayed all the time, and sometimes people park their ships sideways in the Suez Canal, and ships can also get delayed. And for example, in Germany, currently we have a big problem with airport personnel, so lots of flights are also getting delayed. And so we wanted just to ask the question, how should one approach to plan routes in temporal networks if you anticipate that the connections in this network might be subject to delays? So in contrast to the first talk here, the delays are kind of our enemy, and we do not use the delays to our advantage, but we try to kind of route around the delays, so to say. So let me briefly introduce our model. We have, of course, a temporal graph, which is the transport network. And for us, this is a directed temporal graph, since usually a plane going from Paris to London doesn't imply a plane going from London to Paris at the same time. And we have these edges labeled also with durations. So more precisely, every edge has a departure time, which is the time at which let's say the plane departs, a duration, which is the duration of the flight or whatever, and an arrival time, which is the time at which the plane lands. And of course, any two of these determine the third time. And then we further have a starting vertex, which is where we would like to start our journey, and a destination vertex, which we would like to reach. And then we have two parameters for the delays. So the first one is that we assume that we have some numerical upper bound delta, which is the maximum delay that we expect any single edge will have. And then we have a second numerical parameter, which is the maximum number of edges which we will expect that might be delayed. So two brief remarks. In our model, we assume that parallel edges are delayed independently. So if you have two planes going from London to Paris, then we will assume that they might be delayed either, but it has nothing to do with each other. Of course, you could also have a different model. For example, when some unpronounceable volcano erupts, then all of the planes will be delayed. But in our model, we're assuming that all these connections have independent reasons for being delayed, and there might be one plane going, but the other plane not going. And second, if you have any, so we already talked about strict and non-strict paths. In our case, we will assume that if there's any transfer time at the vertices, then this is already accounted for in the duration. So we will assume that the temporal path can arrive at a vertex at some time and immediately depart again. Okay, so now given these inputs I just talked about, then the question we want to ask is, can we get from the start vertex to the destination vertex, even if an adversary would choose which edges to delay? So we have kind of fixed the amount by which edges can be delayed and the number of edges which can be delayed. But now we assume that in a worst case scenario, which edges would be delayed, can we then get from the start to the destination? And it turns out that there's one more important question we need to answer before this becomes a well-defined model. And this is, at which point in time are we informed about the delays? So, and there are three variants we have identified or looked in more closely for this. And the first one is kind of a best case scenario where we are somehow informed of all the delays before we pick our route through the network. So that means the adversary has to pick the edges to delay before we choose how to route from the start to the destination. The second case is what might be considered the most realistic, is where we learn the delays without any prior warning as they occur. So we sit in a train and then this train is delayed, but then we can still adapt our subsequent route. So afterwards we might adjust our route due to these delays and take a different one than was initially maybe planned. And then finally, kind of a most restricted scenario where we have to fix our route before the adversary chooses which edges are delayed. And here, to be specific, fixing the route, by this I mean that we fix the sequence of vertices along which we travel. So of course we cannot fix the exact times, because then any delay would immediately kill our plans. But so here we are required to fix the stations along which we travel before the adversary gets to delay edges. So a possible motivation for this last scenario might be if you're taking maybe you're transporting some cargo through intercontinental flights, and then you need to fill out lots of paperwork for each of the airport you want to have your cargo handled, and then it would be a real hassle if you had to reroute through a different airport, because you would have to redo all the paperwork, and you would really like to stick to your route. And for these three variants, we have the following results. So in the first case, where we get all the delays told up front, we show that you can convert this to a flow problem and solve it in efficiently in polynomial time. For the second version, where you learn the delays as they occur, we show that you can do this by a dynamic programming approach, also in polynomial time. Note here that this v times e times x is actually polynomial in the input size, even though x is a numerical given parameter, because we may assume that x, which was the number of edges which might be delayed in the worst case, will never exceed the overall number of edges there are, because every edge can be delayed at most once. And then we also looked into a variation of this second type of scenario, where additionally we are restricted to never revisiting earlier vertices. And in this case, the complexity takes quite a steep jump, because the problem now becomes p-space complete. Okay, and finally, the last version of the problem, where we fix the route and then the adversary chooses the delays. Here we show that this problem is strongly NP complete. But for example, if parameterized by the number of delays, it can be solved efficiently if this number x is small, so roughly e to the x times poly time. So before I will try to give you a brief overview of some aspects of each of these results. But first, I want to have some technical remarks. First of all, what does it actually mean for an edge to be delayed? So there are kind of two natural choices. The first is that the train is stuck in between stations, so somewhere on the track in between, which means the duration kind of increases of this edge, and naturally also the arrival time. And the second option would be that the train is stuck, already the departure is delayed. The train is stuck at the station. This was the model we have kind of seen in the first talk. And the difference between these two models is that in this option B case, you might get lucky and still catch a train only because it was late, because you arrived late at the station, but the train was also late. So you were able to catch it even though you normally wouldn't be able to. But since we are caring about the worst case scenario, this will actually never happen, just like it never happens in real life that you catch a train only because it was delayed. So you can actually show that with an adversarial setting, both of these scenarios are equivalent, because an adversary will never delay a train if it helps you. So I will just assume that we are working with the first model where the duration time is increased for simplicity. And for the same reason, all delays will always use up the full maximum delay amount delta, because the adversary would gain nothing by delaying by less than delta, since more delay always hurts more than less delay. Okay, so now I'm going through each of our scenarios we considered, again starting with the most optimistic one, where we get told all the delays up front. And as I said, we want to reduce this to a flow network problem. So let's look at a small example. Here we have a very simple network with just 4 nodes. Oops, this is too fast. On the left, we have the start vertex, on the right, the destination, and there are kind of 2 obvious paths here, one via vertex V and one via vertex W. Here, these edge labels are to be understood in the following sense. The black label, 1 arrow 2, means that this edge departs at time 1 and arrives at time 2. And then this edge departs at time 2 and arrives at time 3. So if these both are as scheduled, then we can travel from S via V to D. However, if they are delayed, then we instead use the red label. So here the red label has the arrival time increased by 1. So that would mean our delay amount would be 1. So here, if this edge from S to V would be delayed, then we would still depart at time 1, but only arrive at time 3, and similar for all the other edges. And now how we convert this to a flow problem is by making use of what's typically referred to as the static expansion. So for each vertex in this network, we make a bunch of copies and we label them with the time steps. So for example, for the vertex V here, we have 2 copies, one at time step 2 and one at time step 3. And you could also have one for the other time steps, but it turns out that here only these 2 are relevant. And we take the original arcs from our temporal network. So for example, this one here from S to V, from time 1 to time 2, and we convert it to the temporal expansion in a natural way that it starts at S at time 1 and reaches V at time 2. So these then constitute the 4 black arcs you can see here in the network on the right-hand side. And we do the same thing for the delayed arcs. So if this arc were to be delayed, then it would give us an arc from time 1 to time 3, and these are the red arcs you can see here. So we, in addition to the black arcs, we also add the red arcs, which model delayed edges. And finally, we have the dashed edges, which are just model waiting at any individual vertex, since you can obviously get from vertex V at time 2 to vertex V at time 3 just by staying there for one time unit. And then we assign the following capacities to these edges. We give the solid black edges, which represented the, the original edges. We give them capacity 1, and the other edges, so the red and the dashed ones, we give them infinite capacity. And then it turns out the important observation here is that a set of edges on the left, which whose delay prevents us from going from S to D, corresponds exactly to a cut set containing only black edges on the right of the same number of edges. And so let's look at an example. For example, here, since we have these 2 paths we can take, then an adversary, so it only makes sense to delay the edge from S to V, that this would block the upper path, because if we reach V at time 3, we can no longer continue from there. And the same for the lower path. So if the adversary blocks either of the 2 edges leaving S, then we can just take the other one. But if they block both of them, then we would be stuck. So if the adversary is allowed to block 2 edges, then this is a no instance, otherwise it's a yes instance. And this would correspond to the cut here on the right, cutting the 2 black edges that leave S. So you can check that using only the remaining edges, including the red ones, you will not be able to reach D at time 4. And this is exactly the underlying reason why min cut in the flow network corresponds to a solution to our temporal delay instance, and thus by min cut max flow we can solve our instance by just computing a maximum flow from the start vertex at the first time step to the destination vertex at the very last time. And this of course gives us a polynomial algorithm. So for the second version, so remember, this is the one where you get told the delays basically in real time. So you sit in the train and then you learn that this train is delayed. And it turns out that this can be naturally modeled as a game between 2 players. The first player is the traveler, which tries to get from the start vertex to the destination vertex, and the other player is the adversary, which then gets to choose whenever the traveler has chosen the next edge on their journey, they can choose whether that edge is delayed or not. And the traveler starts at the start vertex at the time 1, and they win if they reach the destination, and otherwise the adversary wins. And then I told you that we had this variant of this delayed routing game where the traveler is not allowed to go in cycles. And in that case, the traveler loses if they ever revisit a vertex they have previously visited. So let's look at a small example, which also illustrates the difference between these two. So here, let's assume the adversary gets to delay one edge by 1 time unit. And let's also assume that the traveler has started the game by taking the blue edge from start to vertex A. Now, if they arrive here on time at time 2, then they can continue via this other edge to D, and the adversary will not be able to stop them. So the only sensible thing for the adversary will be to delay the blue edge by 1 time unit. So the traveler will reach A at time 3. And now they can no longer continue directly to D because this edge has already departed at time 2. So if we were playing the path version of the game, the traveler is now stuck because they're forbidden from returning to S where they have already been previously. So this is then a no instance for the delayed routing path game. But if we're playing the normal version, the delayed routing game, then the traveler can now simply opt to return to their vertex S using this black arc here at the top, and then continue via B to their destination. And since the adversary has already used up their single delay on the blue edge, they can not interfere with this anymore. So this is a yes instance if we are playing the delayed routing game. So let's briefly look at what you need to capture the state of this game. So when we are the traveler and it's our turn, then there's the following information we need in addition to the network, of course, which doesn't change. We need to know where we are currently in the graph. We need to know what time it is, and we need to know how many delays our adversary has left to work with, or how many have already been expended by them. And in the delayed routing path game, it's exactly the same thing, but additionally, we need to know which vertices we have already visited because we're not allowed to revisit those vertices. And given these sets of information, we can, for both games, give a strategy for the traveler by which they can win. So for each edge, we could possibly take next, so which originates at our current vertex and which is in time still reachable for us and which doesn't go to any vertex we are not allowed to revisit again. We look at each of these edges and we test if there's a winning strategy for both of the following cases. If that edge is delayed and the number of delays the adversary can use gets reduced by 1. So this assumes that there is at least 1 delay left. So in that case, we would reach the other end of that edge delayed and then continue from there. Or if the adversary chooses to not delay that edge and their budget remains untouched. And if there's a winning strategy for both of these subsequent positions for us, then we can just take this edge, and no matter what the adversary does, we will then follow either of our 2 subsequent winning strategies and thus can win the game in the end. And now what takes it to computers in practice? So here in the delayed routing game case, you will notice that this state space here, which is made up by the current vertex, the time step, and the remaining delays, has polynomial size because, as I already told you, the remaining delays, so we can assume that these are at most number of edges many. So for the time step, in theory, there could be very many time steps, but we can restrict it to only time steps where actually edges exist, because other time steps we can just basically ignore and skip over. So also this parameter we can bound in a number of edges, and thus this whole state space here has at most cubic size, and we can construct a dynamic programming table containing solutions for all of these states, and thus find a polynomial time algorithm for the delayed routing game. But in the delayed routing path game here, we have this additional part of our state space, which is the set of already visited vertices. And clearly, there are exponentially many possibilities for such sets. And thus, we cannot do this dynamic programming approach. But what we can do is just depth-first search, which will give us a p-space algorithm. And I'm not going to talk about p-space hardness here. So this is everything I would like to say about the delayed routing game. So this brings me to the last scenario. We're out up front, and then the adversary gets to pick delays to try and stop us from reaching our target. And here again, I'm not going to talk about the hardness because it's quite technical, but I would like to imagine that we are given a solution. So let's say we have a route, which again is a sequence of vertices starting with S and ending with the destination D. And now let's look at any prefix of this route. So just a sequence of vertices from V0 to Vi. Then for this route, or for this prefix of the route, we can draw a delay profile. And by a delay profile, we mean this curve I've drawn here on the left, which plots arrival time against number of delays. So that means here on the x-axis, we have all the possible numbers of delays from 0 to x. And for each number of delays, we ask ourselves, what is the worst case arrival time at which we will reach Vi, so the red vertex here, the last vertex of this prefix of the route. What is the worst arrival time at which we will reach Vi if the adversary has this many delays at their disposal? And so here, for example, in this example, we would say, okay, if there are no delays at all, or even if there's one delay, in both cases, we would reach Vi at time 3. And if there are 2 delays at most, then we will be able to reach Vi at the very latest at time 5. And if the adversary has 3 or 4 delays, then we will reach Vi no later than time 6. And now the important observation here is that if we extend our prefix by 1, so going from Vi to Vi plus 1, then we can efficiently compute the delay profile for the subsequent vertex here in blue from the red delay profile. So I'm not going to go over the details because we're already approaching the time limit. So, but I think you will believe me that you can compute the blue curve from just knowing the red curve and knowing the edge labels of this last connection between Vi and Vi plus 1. And this already tells us that the problem is contained in NP because we can then just iterate through all prefixes of the route and compute the delay profiles for them one after another, starting with the trivial route, which contains just the start vertex. And at the very end, we will look at the delay profile for our destination vertex D. And if at position X on the horizontal axis, the arrival time is some finite number, then we know that this is a solution to the problem. But if it's actually infinite, then we know that this is not a solution to this delay robust route instance. And furthermore, we can also use this general approach to find an algorithm parameterized by the number of delays, because you can actually, by a little bit of looking at it, you can figure out that the number of delay profiles existing can be bounded by number of edges times number of delays. And so by doing a dynamic programming table over all these delay profiles at all the vertices, we can solve this in e to the x times polynomial time. So that brings me to the conclusion. So let me just very briefly recap. So if you want to compute routes in a temporal network and there might be delays, then you can do this efficiently if you're given the delays upfront by the flow-based approach. You can also do this efficiently if you don't know them upfront, but you can still adjust your route when the delays occur. So this was the delayed routing game. But there's a restriction here. If you are not allowed to go in cycles, then the problem becomes very hard. And finally, if you need to fix your route up front, then it's efficiently solvable only in special cases, assuming P not equal NP. I told you about the algorithm parameterized by X, the number of delays. In our paper where we looked into this, we also looked at some structural parameterizations. So if you're interested, then please have a look at it. And here are the links to the 2 papers on which this talk was based, one at Stux and one at Sand this year. So thank you very much for your attention.
Thanks for your nice talk. Do we have a question in the room? Yeah.
By the way, I cannot see the chat, so if there are any questions in the chat, then
yeah, I will check the chat and then post.
Just ask a question, maybe you repeat it. If I understand it correctly, you just had one departure per edge. Does it change the complexity if you have multiple departures?
We are not completely sure for some things. So we've only looked into this a little bit. For some things it does not, but we haven't looked into all the variants. So for some it might.
And for which does it not? For the efficient?
So for the last one, I think we were starting to believe that some of the things also hold in the case where you have multiple delays per edge. So there was the route thing where you need to fix your route up front. In the flow-based thing, I don't currently know. And in the game approach, I think in the game it also it's probably a worse complexity, but still polynomial but we haven't written all of this, any of this down really. So yeah.
Okay, thanks.
Yeah, we have another question.
Maybe to repeat it.
Yeah.
Are the problems easier in special graph classes?
Did you heard of it?
So we know that the last one, which is the hardest kind of, where you need to fix a route, is we have a pretty wide range of graph classes where it's still NP hard. So including graphs of path width 3 or something. But you can parameterize this by feedback edge set of the underlying graph. So if your graph is forest-like, that has like not tree width is too hard, but for example, like feedback edge set, then you can find FBT algorithms for this last case. But generally, in many graph classes, it's hard. So including all classes, including a path with 3 graphs.
Okay, do we have other questions? We have someone raising his hand. Maybe you can direct this question.
So I just want to ask, in your delay robust route, you said that we fix the sequence of vertices. Do you assume of the input that if everything is running on time, you never have a faster edge overtaking a slower one? So for example, a high-speed train overtaking a local train. And if you arrive a little bit late because you stated which node you were going to next rather than which edge, you would end up on the slow train because you missed the first fast train, where it would be better to take the second fast train.
No, we don't assume that they're not. So the scenario is also we don't assume anything about the edge labels. Basically, we can have routes edges overtaking each other, and
okay. And does the reduction still hold up if you eliminate such edges? Because I think in your setting, it will never be useful to take the slow local train that leaves before the faster.
Yeah, I think our reduction does not use any edges which overtake other edges.
Okay, thanks.
Okay, thanks again for your talk.
Thank you very much.